Hi everybody, welcome back, and today we're going to talk about section 15.4, doing double integrals with polar coordinates. So we've already done double integrals over general regions, but now there might be some regions that'll be easier to integrate over if we convert to polar coordinates first. So first let's review some polar coordinates. If we have a point in the xy plane, so I have this point here, I can represent that with an x naught, y naught, which is where it lines up on the x and y axis, or I can represent it with a radius, the distance from that point to the origin, which is r naught, and the angle that radius makes with the positive x-axis, which is my theta naught, and those are the polar coordinates. So some relationships between polar coordinates and Cartesian coordinates: r squared equals x squared plus y squared. This is just Pythagorean theorem. X equals r cosine theta, y equals r sine theta. This just comes from trigonometry. If we turn this into a right triangle, then we get these relationships. Theta is arctangent of y over x. That's just using these two equations. And this only works if x isn't 0 and theta is between negative pi over 2 and pi over 2. So if you have an angle in the second or third quadrant, you'll have to do some more work than just using this formula. These formulas always work. This one works in certain cases. Something else in Cartesian coordinates, we usually think of x and y can take on any real values. X can be any real number, y can be any real number. Typically for polar coordinates, we say that r is non-negative, so it's either 0 or some positive number, and theta goes from 0 to 2 pi. Now, there are exceptions to this, and we'll see some of those exceptions throughout this lesson, but typically those are the values we use most of the time. Okay, now let's look at some examples of why we might want to use polar coordinates. So ignore this for a minute. Let's just focus on this region D here. This is a disk centered at the origin of radius 3, and let's say I want to integrate over this disk. Well, if I use Cartesian coordinates to describe this region, this disk is all of the points such that x squared plus y squared is less than or equal to 9. Now, if I wanted to set up bounds of integration, I would have to solve this for whichever variable I'm integrating with respect to first. Let's say I'm going to integrate with respect to x first, so I think about traveling through this region horizontally. Then my lower bound is the negative square root of 9 minus y squared. My upper bound is the square root of 9 minus y squared. And so after I have those x bounds, my y bounds, I just go from negative 3 to 3. So these would be my bounds of integration over this region. But if I think in terms of polar coordinates, I see that my radius just goes from 0 to 3, and since I'm going all the way around, I have the entire disk. Theta goes from 0 to 2 pi. So that's what I have here, describing that region. R goes from 0 to 3, theta goes from 0 to 2 pi. And now what I've drawn here is if I were somehow able to transform this disk from the xy plane to a plane in terms of r and theta, this is the region I would get. So r goes from 0 to 3, theta goes from 0 to 2 pi. I get a rectangle. This is what's called a polar rectangle. And if you remember when we first talked about double integrals, integrating over rectangles is the easiest thing you can do. You can switch bounds. You don't have to worry about coming up with functions, everything. All your bounds of integration are numbers. So this is a much easier integral in polar coordinates, at least in terms of what you're integrating to. Instead of these functions, all of my integration bounds are just numbers. Look at another example. So here is half of an annulus, or half of a washer shape. If I wanted to integrate, or first let's just describe this region in terms of Cartesian coordinates. I have that this is between the region between two circles. It's between the circle of radius 2 and the circle of radius 4. So that means x squared plus y squared is between 4 and 16. And I'm only in the upper half plane, so y is greater than or equal to 0. Now, if I want to start describing this, if I want to actually integrate and set up the bounds of integration with Cartesian coordinates, this is going to be very difficult. And you see I already have some dashed lines drawn here, so let's go through why those are there. Let's say I want to integrate with respect to y first. If I want to integrate with respect to y first, I think of moving through this region vertically. I have 3 different lower bounds, right? I have a lower bound here, and so I'd set up one integral for this region. I have a different lower bound here, this half circle, and so I'd need another integral for this region, and I have another lower bound here. so I need an integral for this region. If I want to integrate with respect to y first, I have to set up 3 integrals. Well, what about if I want to integrate with respect to x first? So I think about traveling horizontally from left to right. Well, here, at this red dashed line, my right curve changes. Right? So I'd need one integral for this region. Then my right curve changes here, so I'd need another integral for this region. And I've left out this region, so I'd need a third integral for this region. So if I integrate with respect to x first, I still need 3 integrals to integrate over this region. And the bounds are all going to be functions, except for this one. That's just going to be y equals 0. So it's going to be difficult. Now, if I convert to polar coordinates, r is just going from 2 to 4, because my radius goes from 2 to 4 in this region, and theta goes from 0 to pi, because I'm only getting the top half of this annulus. So this is another polar rectangle. My bounds are just numbers. R goes from 2 to 4, theta goes from 0 to pi. If I were to transform this into an r and theta grid, you see I have this rectangle. So it's much easier to integrate over these regions in polar coordinates. Another issue we need to address before we can start doing examples is dA. So when we do a double integral, we have this double integral over region D, some function dA. In Cartesian coordinates, dA is just dy dx or dx dy. But in polar coordinates, we're not just going to get dr d theta or d theta dr. Something else is happening. So to derive this, to explain what's going on, let's take a look at a polar rectangle. What I have here, I split that polar rectangle up into smaller polar rectangles. And so in particular, if we take a look at this, let's see if I can find the area of this small region here in terms of polar coordinates. And then I'll think about what happens as I make that area infinitesimally small. So, the idea here is that I want to find the area of this region here. So the way I'm going to do that is by finding the area of this sector of a circle and subtract the area of this sector of a circle. So if I take the area of the larger sector, subtract the smaller sector, that's just going to give me the area of this little region that I want. I'm going to call that delta A. So I need to know the formula for area of a sector. It's theta over 2r squared, where r is the radius of my sector and theta is the angle in between where I start and stop my sector. So for this sector, the difference between my angles inside this sector I'm calling delta theta, and I actually have 2 different sectors, so I'm going to need some way of describing these 2 radii. And so one way is just calling them r0 and r1. So r0 is the radius of the smaller sector, r1 is the larger sector. So then my delta A, the area of this region, is going to be delta theta over 2 r1 squared, that's the area of the larger sector, minus delta theta over 2 r0 squared, which is the smaller sector. But now I have these 2 things that neither of them are in terms of delta r, which is the length of this region in the radius direction that I want to consider. So what I'm going to do to get around that is I'm going to pick a radius right in the middle of this region. So that's this r that I've picked here. I've drawn it again here and say, okay, this r is halfway between r0 and r1. So now I can describe r0 is going to be r minus half of this delta r. That gives me r0. And r1 is this r plus half of this delta r. That gives me r1. And so now I can rewrite delta A, replace r1, this value, with r plus half of delta r. And now I have, that's my r1. My r0, instead of saying r0, it's going to be this r minus half of delta r. And so that's my r0. And so now this is all in terms of delta theta, delta r, and this r I've picked halfway between r0 and r1. And so now this is the area of this region, this delta A, is this difference. So now I just have to do some algebra, square these things. I can factor out the delta theta over 2. And once I square both of these terms, this is what I get, and I start canceling things. This r squared cancels with this minus r squared. This delta r squared over 4 cancels with this minus delta r squared over 4. And I'm left with r delta r plus r delta r to give me 2r delta r, and I can cancel out the 2. And now if I take this, so this is the area of this region that I considered. And if I take this area to be infinitesimally small, This delta r becomes an infinitesimally small radius. This theta becomes an infinitesimally small angle. But the r doesn't change. So dA is actually r times dr d theta. Or I can say r times d theta dr. I can switch either of these two. Now this derivation isn't entirely rigorous. This was just a way to explain where this change comes from. There are some other technical details to make this entirely rigorous. Like for instance, can I explain this without taking this r directly in the middle? Yes, but it requires some more details that I'm not going to go into now. But for now, this was just to give you an idea of where this r comes from. The main thing you need to remember is that when you switch from Cartesian to polar coordinates, you have to multiply your function by r. So dy dx is r dr d theta. Whatever you're integrating gets multiplied by r. So for instance, if I'm integrating some function f, and it's in terms of Cartesian coordinates, if I switch to polar, I need to replace all the x's in this function with r cosine theta. I need to replace all the y's in this function with r sine theta. I need to multiply by r, and then I can integrate. Okay? So the area of a region, we know, is just integrating 1. But in polar coordinates, that's not true. If I want to find area in terms of polar coordinates, dA is r dr d theta. So area in polar coordinates, I'm integrating the function r, and that gives you the area of a region. So it's slightly different. All right, now let's take a look at an example. Let's say I want to evaluate this integral x squared plus y, where d is the annulus between the circles x squared plus y squared equals 1 and x squared plus y squared equals 5. So first, let's take a look at this region that I've crudely drawn here. It's just the region between two circles. The inner circle has a radius of 1. The outer circle has a radius of square root of 5. If I wanted to describe this region in Cartesian coordinates and set up bounds of integration, I would need to set up 4 integrals. And you can look at that and see if you can see why I would need to set up 4 integrals. In polar coordinates, however, this is another polar rectangle because r just goes from 1 to square root of 5, no matter where I look. And theta goes all the way around, so theta goes from 0 to 2 pi. So I get these bounds in polar coordinates, and it's a much easier integral. Now, before I'm ready to integrate, I have to convert the function I'm integrating into polar coordinates. X squared plus y becomes r squared cosine squared theta plus r sine theta, because I replace x with r cosine theta, and I replace y with r sine theta. So this is the function I want to integrate in polar coordinates, and you have to remember when I set up this integral, I need to multiply by r. So here's my integral. I'm integrating from 0 to 2 pi in theta. I'm integrating from 1 to square root of 5 in r. And then there's my function multiplied by r. Whenever you change to polar coordinates, you've got to multiply by this r. Now let's go ahead and start integrating. I'm integrating with respect to r first. First, let me distribute this r so I can look at what I'm really integrating. If I distribute this r, I get r cubed cosine squared theta plus r squared sine theta. And now I'm going to integrate with respect to r first. So I integrate r cubed to get 1/4 r to the 4th. I integrate r squared to get 1/3 r cubed. And I'm evaluating from 1 to square root of 5. When I plug in square root of 5 here, square root of 5 squared is 5. So this is really 5 squared, which is 25. So I get 25 over 4. When I plug in square root of 5 here, that's square root of 5 times square root of 5 times square root of 5, I get 5 root 5 over 3. And then I plug in 1, so I get minus 1/4 cosine squared minus 1/3 sine. I can combine like terms. 25 fourths minus 1/4 gives me 24 fourths, or 6. And then 5 root 5 over 3 minus 1/3 is 5 root 5 minus 1 over 3 sine theta. So now this is the integral that I need to evaluate in theta. And the sine term is fine. I need to look at this cosine squared term. I'm going to use the trig identity, cosine squared equals 1/2 plus 1/2 cosine 2 theta. Plug that in and then integrate. So these trig identities are going to be your best friends when you're doing integrals in polar coordinates because cosines and sines come up quite a bit. So I plug 1/2 plus 1/2 cosine 2 theta in, distribute the 6. That becomes 3 plus 3 cosine 2 theta, plus this term hasn't changed at all. It's 5 root 5 minus 1 over 3 sine theta. I integrate. 3 becomes 3 theta. I do this substitution here, or you can think whenever I have a constant times my variable, when I integrate, I need to divide by that constant, right? So I integrate cosine to sine, and I have to divide by this constant, which is 2. That gives me 3/2 sine 2 theta. You can verify that yourself by working out the u substitution, and so you would get exactly the same thing. And then sine integrates to negative cosine, so I get negative 5√5 minus 1 over 3 cosine theta, and I'm evaluating from 0 to 2 pi. So now I plug in my bounds. I get 3 times 2 pi plus 3/2 sine of 4 pi minus 5√5 minus 1 over 3 cosine 2 pi minus 3 times 0 minus 3/2 sine of 0 at sine of 0 plus 5√5 minus 1 over 3 cosine of 0. So now a bunch of these things go away. Sine of 4 pi is 0. This is 0. Sine of 0 is 0. Cosine of 2 pi is 1, so I get negative 5√5 minus 1 over 3. Cosine of 0 is 1, so I get positive 5√5 minus 1 over 3. These two things cancel out, and my answer is just 6 pi. And we're done. Now, before we go, we could have just evaluated the double integral of x squared and gotten the exact same answer. So in other words, I could have just ignored this plus y. Why is that the case? If you remember our discussion about odd functions and symmetric domains, then I could first split this integral into the integral of x squared plus the integral of y. Y is an odd function. This domain is symmetric with respect to y. Odd functions over symmetric domains are 0. So I can just ignore that term and just integrate x squared. I would have gotten the same answer. And I might say, well, x squared is an even function, and this domain is symmetric with respect to x, so could I have just multiplied by 2 and integrated over half of this region? Yes, you could have, and that would have changed your theta bounds. So instead of integrating from 0 to 2 pi, if I just look at half of this region, that would have been negative pi over 2 to pi over 2, or you could have done pi over 2 to 3 pi over 2. So you'd have to change the bounds in terms of theta, and remember you'd also have to multiply that integral by 2. It gets a little more complicated when dealing with these even functions and symmetric domains with polar coordinates, so you might just want to just integrate x squared. And remember, you don't have to do any of that. We didn't recognize any of that before we started this example. We just went ahead and did the problem without looking at symmetry and even and odd functions and just worked it all the way through, and we got 6 pi. That would be the answer no matter how you did this, as long as you did it correctly. All right, in the next video, we'll finish up section 15.4 by doing a couple more examples.